like to welcome everyone to our next session. It's titled Defending the Planet from Asteroids and Solar Flares. And joining us today are two incredible guests, Dr. Nicola Fox, and she is the Heliophysics Division Director in the Science Mission Directorate at NASA headquarters in Washington, D.C., and Mario Juric, who is the professor of astronomy and the director of the Data Intensive Research in Astronomy and Cosmology Institute at the University of Washington. My name's John Wells. I produce and host for Cool Science Radio. It's NPR's KPCW in Park City. I'll be leading this conversation for about 45 minutes, and then we're going to go to your questions. If you have any questions for our speakers during this conversation, please drop them in the chat, and we will hopefully get to all of your questions. Nikki Fox, we will start with you. Can you tell us what heliophysics is and why it's so important?
Yes, I would love to. So I'm going to actually quickly share my screen. I'm going to be brave and try and do that because I've got a nice graphic here that kind of, I think, really sort of gives you an idea of the realm of heliophysics. And so heliophysics is basically everything under the sun. And so we study in the heliophysics division everything from the core of the sun, or in the solar interior, all the way out to the very edge of our heliosphere, or our sort of protective bubble. The sun, it not only is it a beautiful sight in the sky and a star and our nearest star and all those really great things, but it actually protects us, it protects our solar system from the vagaries of interstellar space. So out beyond all of the planets, out, beyond even Pluto and beyond all those dwarf planets, there is this sort of very protective kind of boundary. And that's where our solar wind, or the atmosphere that continually streams away from the sun, that's where that kind of tapers off and we get into interstellar space. But it actually forms like a protective boundary for us, like a cavity as we orbit around in the Milky Way. And so in the heliophysics division, it is our job to study every single aspect of that realm. And so we do that with a wonderful array of spacecraft. And you can see all those spacecraft there. We have 20 missions that are currently operating on orbit. We have 12 missions that we have in formulation. So we've just recently selected them and they've started building them. And then we have one understudy, which I circled there, which is a new mission that we're still in the sort of formulation phase before we actually send it out for people to bid on.
So not only does the sun sustain us and bathe us in its atmosphere, the planet Earth, the other 7 planets, the dwarf planet Pluto, and everything else in the solar system, we're all in the atmosphere, but it is our protector. And I just find that fascinating. And of course, the galaxy is expanding and everything is moving. So that's just really interesting to get your head around. I wanted to ask you that up until 1859, we didn't know that events that occurred on the sun would affect our planet directly. Can you talk a little bit about the Carrington event and what happened in August 1859?
Yes, I can. And so I'm going to put some solar footage up here so you can kind of see what I'm talking about. But the sun is an extremely, extremely active star. And I'm hoping this actually plays for me. But the sun is continually changing. And so as you look on here, you can see some sort of loops that are sticking out from the side of the sun. And unfortunately, the video doesn't seem to be playing for me. But I can force it to play. There we go. So you can see these loops kind of are sort of changing. They are getting larger. They're getting stretched out. And they can then explode and send billions of tons of this coronal material out into the interplanetary space, and often it comes towards us here at Earth and it can cause problems. But we only found that out, as you correctly said, in 1859. And that was a young British astronomer, Richard Carrington, was staring through his brass telescope. He was sketching sunspots, which he did every day to track the progression of sunspots as they moved across the sun. And he saw there was a particularly large group that he was following. And while he was actually looking at it, he saw what he described as 2 bright white flashes of light around this sunspot. And so he rushed away to get a colleague to say, come back and look at this amazing thing I've just seen. And by the time he got back with his colleague, there was no light. There were no bright flashes of light anymore. We now know what he saw was a solar flare. Didn't think much more of it, but then just a few hours later, the compass needles at Earth kind of began to oscillate violently. The aurora was seen down at very low latitudes, much, much lower than people who'd never seen aurora before, that suddenly an aurora in their sky. And the telegraph system in the US, they had sort of sparks that actually flew from the telegraph system. The whole system went down for a number of days. And that was the first time that we knew that something that was happening on the sun actually had such a profound effect on what we have here at Earth. And so that was really the first time that we knew this was happening. It's kind of, when you think people looked up at, the very first people looked up at that bright light in the sky and wondered what it was. And so to a certain extent, we've studied the sun since the dawn of time. And yet it took till 1859 for us to realize that we were sitting in the path. You commented that it really protects us. It's our protector against the vagaries of interstellar space, but it also has the power to really cause dramatic problems for our technology here at Earth. And in 1859, the telegraph system went down for 4 days. And you can imagine, if I'm talking to school kids, they kind of go, so what? Then I say, well, just imagine if you couldn't have the internet and you couldn't play video games and you couldn't do any of that for days or weeks or months, and sort of panic usually ensues in the classroom. But it really just is it shows we rely on technology so much more today than we ever have before. If you just think back to even 20 years ago, if you wanted to make a phone call, you really used that rotary dial thing on the kitchen wall, and that was all. And now, you have an iPhone that you hold in the palm of your hand that you probably use it for everything almost except for making a phone call, because I always feel like if I have to make a phone call, all other forms of communication have failed. But you think there would be city blocks worth of computers that would have been needed to actually do the type of communication that we're used to now. And so as we become more and more reliant on spacecraft, on GPS, on power grids, on everything that we do, we are so much more susceptible to things coming from the sun.
Well, we're certainly going to talk about monitoring an early warning and how we can protect ourselves in the future and be able to shut down grid, reposition satellites, those sorts of things. But I wanted to touch on one other piece of history, and then we'll go to Juric. And that is, in July of 2012, a solar superstorm generated two CMEs, again, colossal mass ejections of plasma. They were very large, and they crossed the Earth's orbit. They missed our planet by 9 days. Can you tell us about this event and what we learned from it?
Yes, and I actually managed to pull that up for you.
Oh, beautiful.
So this is actually the event itself, and you were absolutely right. Happened in July 2012, and it was the most intense storm that was observed since that Carrington event in 1859 that we just talked about. This one did not impact the Earth. It actually went off the side. It's a very complex event. There's actually sort of two CMEs, or two coronal mass ejections, that go off. Sort of one goes and then another kind of clears out space, and then the second one comes and is super effective. It actually impacted one of our stereo spacecraft, and so you're seeing a sort of head-on event coming towards the stereo spacecraft. We're very lucky that it did hit the spacecraft, because we were able to get the data about this event. Had we just been sitting here at Earth waiting for something to come to us, we would have completely missed how huge this event was. So we were able to take the data and then model what that would have done had it actually come directly towards us here at Earth. And you can see it was accelerating away from the sun at a huge, huge speed. And it would have arrived at Earth in just about 15 hours. Now, the normal travel time of the solar wind from the sun to the Earth, it's 93 million miles. It travels at roughly 1 million miles a second normally. So it takes 93 hours, or 3.5 days to get to us here at Earth. This would have got here in 15 hours. That makes it much tougher to predict. Had it happened 9 days earlier, this would have been a direct impact to us here on Earth. And so we would have been looking at definitely Carrington level event here on Earth. It's significant for us because if you only are observing by, waiting for something to come and hit us at Earth, you may miss a lot of the events. Now we have spacecraft that are able to sometimes see the backside of the sun, see off the sides of the sun. We're able to determine that these large events are happening much more frequently than maybe the 150 years we thought beforehand.
And please correct me if I'm too sensational on this, but I understand that transformers are all custom builds and they take upwards of a year to build. Had we had transformers knocked out and we would have to wait a year to get electrical service restored, I'm not going to say Mad Max in the Thunderdome, but what sort of challenge would there have been for us?
So, here's just this was a study that was done that says, if we had these big events and we had an electricity blackout, so a power grid goes down, that the daily economic loss in the US would be $41.5 billion. So that's a day, an additional 7 billion through like the international supply chain. And that's just with the electricity blackout. So you're absolutely right. If you lose a transformer, that is a very serious impact. Now, what we try and do, of course, is we want to predict these events. And so if you can predict and you can put out early warning, and NASA sort of has the mandate to do all the research to sort of push the boundaries and improve what we can do with our space weather data. Our sister agency, NOAA, has the mandate to actually do the predictions of the storms for all of the commercial companies. And so we work very closely together to be able to actually put out a warning, hey, we think this is going to happen, so that companies can actually take precautions. Maybe you take down a power grid in an orderly manner. It's a pain, you're without power for a few hours, but once the worst part of the storm is past, you can bring that power grid back up without any damage to it. If it just gets impacted at full power, that's when you have problems for your transformers. And so that's why it's so critical that we are able to really predict these events.
Nikki, that was a great explanation. Thank you. Mario, it's great to have you with us as well. Can you give us an overview of where we are today and our ability to observe and track near-Earth objects?
Yeah, definitely. Let me share a visualization for you first, and I think they'll bring this point across. So one thing that I always like to start with when we discuss near-Earth objects and potential impacts from above is this. As Douglas Adams says, don't panic. What I'm about to show you looks scary, but these are events that are very rare and not something to worry about on a nightly basis. This is something for us to worry about as humanity on timescales of tens or hundreds of years. So the kinds of objects that we're looking at are small rocks, asteroids, that sometimes cross the orbit of the Earth and impact. And here, what I'm showing you, the scary video, which is why I wanted to open up with Don't Panic, is of an event that happened over Russia on February 15th, 2013, so almost 10 years ago now. They were very small objects. They're just a 20-meter asteroid, 12,000 metric tons, entered the atmosphere at a shallow angle, as you can see here, at 20 kilometers per second, and produced a blast equivalent to 500 kilotons over a place in Russia's Far East called Chelyabinsk. So that generated 1,500 injuries. These are counted as people who were, either cut or bruised or hurt enough to go ask for help either in doctor or hospital, and damaged about 7,000 buildings. And this was a small object. It turned out we were lucky at the time because it entered under the shallow angle and exploded fairly high in the atmosphere. So this blast wave dissipated by the time it came down to the ground. But you can imagine if an object like this came at a bit more direct angle, not over a place that has 100,000 inhabitants, but maybe over a larger city with millions. That is something that could potentially be quite worrying and result in
of course,
economic damage or people getting hurt. Go ahead.
Yes, so there are asteroids that are 20 meters in diameter, like the one you just talked about that exploded over Russia 10 years ago. And at the other end of the spectrum are the civilization-ending asteroids that are 1 kilometer in diameter and larger, like the one that killed off more than 75% of Earth's species 66 million years ago. So my question is this: how many asteroids of varying size are near-Earth objects? What's your sense of what percentage have not been identified yet? And how do we track them?
Yeah, so great question. The Chelyabinsk one is concerning, but it's still relatively small. The larger ones, like the ones that impact that wiped out the dinosaurs, or roughly objects that are larger than a kilometer that could potentially impact the Earth, there are an order of 1,000 of those. And the great news here is that we essentially know where nearly all of them are. So 93 to 95% are now known, they're tracked, and we know that they're not going to impact over the next couple of hundred years. So I think we're, from the point of view of a large, massive extinction event, as like the one that's happened 60 million years ago with dinosaurs, we know, due to a number of surveys that NASA and their partners started back in the 1990s, we know we're generally fine. The smaller objects, though, is where the front line of research is right now. If you get an object the size of 140 meters or so think 500 feet in diameter, such an object would cause continent-wide destruction and tremendous disruption to civilization, as you can imagine. The picture is not as rosy. We know only about 30% of those, and we would like to bring that number up by a factor of few, so that again we have some confidence that something like that is unlikely to happen. And then when you start going down the size scale, this is like size or mass is really what matters here. If you go down the size scale, you get into objects like the ones that hit over Tunguska 100 years ago. Those we know probably less than 1%. And if you get down to Chelyabinsk, then essentially we don't quite know where those objects are. And for those objects, we might never know where they are just because they're too small to track. We might want to adapt slightly different strategies to mitigate them. But yeah, there's good news, but there's a lot of work left.
Well, short of Bruce Willis beating up an asteroid that's in our path, what are our non-Hollywood diversion strategies?
The most important strategy is find them. It sounds silly, but every single strategy that we come up with depends on knowing that this object is going to impact decades in advance. Examples of such strategies are the simple one: hit it with something. NASA's DART mission is on the way to an asteroid right now and is going to test this approach, where an asteroid is going to be hit by a small impactor, and we will observe it from the Earth to see how much its orbit changed. The idea here is, if you know that there's an asteroid heading right for us some 50 years from now for an impact, if you nudge it just a little off of its orbit now, during those 50 years, that little nudge will accumulate, and miss the entire planet. So the critical thing here really is to find them as early as possible.
Yeah, exactly. We're going to talk a little bit more about strategies, and the DART mission. We'll come back to that, which will be our first collision with an asteroid to see if we can nudge it. And we'll talk about that in a couple of minutes. Nikki, I wanted to go back to you for a moment. You have 20 operating missions, 27 spacecraft. You have missions in development. You have missions in long-term formulation. I'd like to pick my favorite spacecraft, which is Parker Solar Probe. Can you tell us about this amazing spacecraft?
I certainly can. And in fact, as you may imagine, it is also my favorite mission. So yes, let's just see if I can share. There we go. So this is just obviously a graphical representation of what the spacecraft looks like. So Parker Solar Probe is the NASA mission to touch the sun. And many of you may have seen all the press activity at the end of last year when we actually finally went into the inner corona. We actually went below the transition region where everything that's very close to the sun, all of those sort of plasma loops that you see are actually rotating with the sun like one solid body. And then there's a transition region where, in fact, the intense heat. And so one of our mysteries is that the corona or the hazy atmosphere that you see during a total solar eclipse is actually 300 times hotter than the visible surface of the sun. And where we see this sudden increase or this sort of maximum temperature, the plasma itself actually gets really energized, and so it can accelerate away from the sun, and that's what we call the solar wind. And so there's a region where it transitions from rotating with the sun to moving radially outwards, and that is a very important, it's one of the critical regions that we study in the sun. And for the first time we actually put a spacecraft beneath that, so that was very exciting. And I'm not, let's see if this will run. So this is just a nice, this will show you, it starts with launch that happened August 12th, 2018. You see a very beautiful Delta IV Heavy majestically lifting off the launch pad at 3:31 in the morning. Very, very beautiful sight. And you see that lifting off there. And then if this is now obviously a representation, but here is the fairing parting and letting the spacecraft out into space. We had a second stage there, cryogenically fueled second stage, which gave us another boost. And then you'll see our custom built upper stage giving us, that's a kick motor, giving us our final Delta V as we leave the planet. There the spacecraft is separating, and the first thing that we do is put out the solar panels to make sure that we have power to the spacecraft, and then we deploy some of the instruments. So you see there's the magnetic field instruments coming out the back there, and then the plasma wave or the radio wave antennas coming out the front. We're moving very fast. So about 6.5 weeks after leaving Kennedy, we flew past the planet Venus for the first time. We are very generous in the Heliophysics division. We give energy to the planets. We don't take it like some of those other planetary missions. I'm just kidding. But we actually use Venus to kind of slow us down a little bit. We use it a bit like a handbrake turn. And so we turn the orbit and focus it on the sun. And then as we get close, we tuck those solar panels in because we don't want them to get too hot. And we do successive flybys of the sun. Venus is important for us. Every time we are able to fly past Venus, we can actually trim our orbit a little bit more. And so essentially we sort of take some steps closer and closer to the sun. And we'll do 7 Venus flybys in the course of our 7-year mission. We've actually just done number 5. And after that, we have another 2 to go. So we're getting to our closest approach. Right now, we actually just came out of perihelion number 11 this morning. And we got some, yesterday, we got some data down last night, and we know that the spacecraft's all okay. So her current distance from the sun is about 5.3 million miles from the sun's surface. Again, the Earth is 93 million miles away. We'll go into a final perihelion configuration of 3.9 million miles away from the sun's surface. And to kind of put that into perspective, if I put the sun and the Earth on either side of a football field, I'll pop Mercury in at the sun's 35-yard line and Venus at the Earth's 28-yard line. Up until the launch of Parker Solar Probe, the record for getting closest to the sun was held by Helios 2. So you're seeing there some of those coronal loops coming out to 15-yard line. Helios 2 actually went in as far as the sun's 29-yard line, so inside the orbit of Mercury. But if we welcome to the stadium Parker Solar Probe, the newest mission to study the sun, she will tuck and run all the way to the 4-yard line. And so I think that gives you just a really good idea of just how close to the sun we are. And I'll finish by showing you some data that actually very few people have seen. So this is a special treat for you. And again, this is from actually perihelion number 10, which we did in November of last year. And you'll actually see some of those really big coronal mass ejections. They're actually not that big, but we're so close to the sun that they look huge. They actually do smear out as we get further away. But you can see actually, number one, the sun is waking up. It's getting very much more active. And there's a beautiful event now, which is a compound event. You'll see 1, 2, 3, and 4 little coronal mass ejections that went off. And then they'll actually form a larger event as it gets further away from the sun. But being so close, we're actually able to now sort of dissect almost the anatomy of a coronal mass ejection and really find some of those features that we've never been able to see before, because we're always looking through the atmosphere between us and the sun. Now we're right in that atmosphere below that transition region and really studying the corona for the first time.
And for our conference attendees who are watching this and wondering why this incredible spacecraft does not burn up when it goes through the corona, that forward edge is a graphene sandwich board, very sophisticated, that is 2,500 degrees on the sun side. It's roughly 90 degrees on the instrumentation package side. So it protects everything. Okay. Mario, back to you. Can we talk about the DART mission and what we're going to hope to learn from that?
So DART is a NASA mission that launched towards asteroid called Didymos, and is designed to test some of these mitigation strategies. So this asteroid is special because it is actually a double asteroid. So it has a small moon orbiting it. The moon is called Dimorphos, and when you have something in orbit, the nice thing about it is if you hit that thing that is in orbit, you can observe how the orbital period changed because of that impact, and that will tell you how much of the energy of the impactor has been transferred over to the atmosphere, over to the object. So that's the idea of this mission. The idea is not to actually hit the big asteroid, but to hit its small moon, and then from the ground with telescopes observe how much did that move? Did that impact change its orbital orbital period? And the idea is that, or the thinking is that the change is going to be somewhere in order of 10 minutes or so. And the reason why this is important is you might think, this is basic physics. You have an object, you hit it with another object, the momentum transfers, and then the two objects go off of as one, you can calculate it. But it's not as simple because this asteroid is not a solid body. We don't actually know what happens when you hit an asteroid. If it's kind of like a rubble pile, some of it may split off, and you may have this recoil effect from all the ejecta. So you actually transfer even more momentum than you expected. If it doesn't, you transfer less. These kinds of things are extremely important if you're trying just to nudge the asteroid off of its orbit so as not to hit the Earth. So we need to know it in advance. So this mission will tell us a little bit about what happens when you actually hit an asteroid, and how much do you move it.
And you and I both talked about this before. We had both heard about it from two different areas. I had heard about it from JPL as they were looking at new ideas. And JPL was evaluating a proposal to paint the sun side of an asteroid in our path with some kind of white powder that would absorb the sun, again on the sun side, and the reflection of sun versus absorption might change the trajectory slightly. I don't know if this has gone forward or not. Have you heard anything about it?
This is quite a serious proposal. It hasn't, these kinds of tests haven't been done, but the general idea is if you change the reflectance properties of an asteroid, you change the way it absorbs heat, you change the way it reacts to pressure of sunlight coming from the sun. And that can create a little bit of an additional thrust on that asteroid, which again, with 50 years advanced warning time, might shift it off its orbit. It hasn't been tested yet, but it's quite it's something that's quite feasible, possible, and non-destructive. It's easier to bring with you a couple of tons of material to paint something than to essentially construct a bomb or something along those
Yeah.
lines, which are some of the other proposals.
Right, exactly. Okay. Nikki, I do want to talk to you about monitoring and early warning for CMEs, but I want to cover one small piece of history first. We talked about Carrington in 1859. We talked about the 2012 large CMEs that were pretty scary. But I want to talk about something that happened a month ago, February 4th. There was a geomagnetic storm that, well, I'll let you talk about it. Can you tell us about that?
Yes, absolutely. We had actually, it really wasn't thought to be a very big event at all. It was a very, very, very average storm, nothing really out of the ordinary. The thing that was maybe different was we'd actually had an event that had been going for a little while. It had kind of cleared out a lot of the ionosphere thermosphere, or like the upper region of our atmosphere. So we saw this coronal mass ejection on January 29th. It was not moving very fast. We were just having a chat in the chat box there about how fast an event can move. This one wasn't moving very fast at all. We actually saw the event, we identified it, and I even said, well, that's not going to do much. It's not, it's going to take 4 days to get here. Good Lord. But it actually did do more. It actually drove significant energy into the upper atmosphere. And so this actually shows how you really need to know a lot of different aspects of these events, because if you only look at what's coming from the sun alone, you can, like I did, sort of flippantly say, oh, it'll be fine. The event happened, it drove a lot of energy into the upper atmosphere, and it changed the orbital drag environment. And so during this storm, about 12 hours into the storm, SpaceX actually launched their Starlink satellites. And at this time, the thermosphere itself had undergone significant heating and expansion. And so what it had done is it actually sort of raised the orbital drag environment significantly. And SpaceX does a great job. They actually launch they go low when they launch their spacecraft, because if there is an issue, they will quickly re-enter and not cause any debris. But the downside is it takes them a while to actually get up to where they need to be. And so when they launched, they were in a much higher drag environment than they had anticipated to be. And so they actually, instead of being able to overcome the drag, they actually were not able to. And so they lost, there's a projected loss of about 40 satellites. And it was only a minor storm. And so we see these storms probably once a month, more frequent as we get towards solar maximum. These larger storms will happen more and more. And again, if you sort of contrast the way we are changing our technology and the way we're changing our environment, the last solar maximum, 11, 12, when was it, 2012-ish, there was no big Starlink network at that point. So we, even as recently as the last solar maximum, we haven't had this kind of technology that we have now. And so working to be able to predict and to help find a model and actually find something that's operational that would actually help predict these things and help the sort of new space operators be able to operate through these events. Again, what we want to do is do the prediction and help them to be able to operate through them and not have catastrophic failures.
Okay, and before we go back to Mario, if you could tell us a little more detail about the observation, the early warning, giving this data to NOAA, and then NOAA will already have red phones and things with various grid operators and satellite operators to do repositioning.
Yes, NOAA does a great job of doing these predictions, and we work hand in hand with them. We fund a lot of research that really is geared to better enabling predictions. So, what are the game-changing measurements that you need to do? What would be the new measurements if you added them to existing models that would improve their accuracy, for example? Whole new missions. So I said we have one mission under study. It's called the Geospace Dynamics Constellation, and it would be 6 small spacecraft that will actually go kind of as a constellation. They'll start off close together and then they'll spread out over time to look at what's happening in our ionosphere thermosphere system. One thing that we've learned very recently is that terrestrial weather also has a big impact on space weather. There's actually a sort of interaction between space weather from above, terrestrial weather from below, and you get, interaction between them. And so you sort of get bubbles and things that form in the thermosphere that can cause all kinds of problems for communication signals, for example. And so we really need to better study this area. Orbital drag, we're going in the area where these spacecraft would have needed that data. And so we're already now planning ahead. Okay, we're going to get this new mission up in a few years. What are the models that are going to take advantage of this new data? How do we couple them with the models that we use to predict now and sort of add another tool that's available for NOAA? And then we work with NOAA. They have a sort of test bed, a framework, and we actually can put our results into their framework and see if they, how they work in the operational environment. So it's a really great partnership.
Yeah. Mario, can you tell us about LSST?
Yes, it's LSST is of course a cautionary tale of what happens when you let an astronomer construct an acronym. It's a telescope, it's an observatory, it's a survey, and I'm showing the photo of it on my screen. It stands for the Legacy Survey of Space and Time. But the idea is what we've been doing over the last decade or so is there's been this realization that one of the things we're missing, not just in asteroid science, but in astronomy in general, to answer some of these big questions like what is a dark energy, what are the potential impactors, what is the census of bodies in the solar system, we need more data. We need extremely large telescopes that don't just go deep, but they go wide as well. We want to, in effect, download the entire sky into databases and then analyze it. And that's what LSST is. It's a new observatory that's just about to be finished in Chile, called the Rubin Observatory, that will repeatedly image the sky for about 10 years. It will generate some 60 petabytes of raw data. It'll image 40 billion stars and galaxies and asteroids. It will generate 30 trillion observations. So each one of these objects is going to be observed roughly 800 times. And with the addition of LSST, you know how I've been saying the most important thing about threats from asteroids is to know that one is heading our way decades in advance. That's what LSST is going to do. We will discover some 80% or more with the addition of LSST of asteroids larger than 140 meters. That basically cuts down our risk by a factor of 4. And then we can also go further down. We can start looking at objects the size of Tunguska, the size of Chelyabinsk, and so on and so on. But I think this is probably one of the most exciting things that's happening in astronomy. It's coming online in about 2 years. Phenomenal, interesting data analysis problem. How do you analyze 60 petabytes of imaging data? How do you find all these asteroids? And something that is really crystallizing how much collaboration there needs to be these days between both astronomers, engineers, and computer scientists to pull off missions like this.
Mario, we have a number of observatories which are out in space that are observing and tracking and helping us out. Rubin, as you speak of right now, is terrestrial based. It's there are people in astronomical circles who are saying that it's getting more difficult to view from the planet because of all the satellites and those sorts of things. Is it a problem today? Will it be a problem in the future? Do we need some sort of international get together on this?
Yes. So I think this is something that Starlink has really brought into focus. As there are more and more satellites in Earth orbit, the chance of them crossing the field of view of a telescope while it's taking an image or photobombing us becomes larger and larger until it essentially hits 1. So like every image you take has a trail. We've actually had a quite good relationship, or developed quite good relationship with SpaceX. They are engineers primarily, and they love to solve problems. They've worked with the Rubin Observatory project to mitigate some of the brightness of satellites that they're launching. So I think with combination of that and the combination of some software mitigation features that we're going to develop, I think Rubin is not going to be tremendously impacted by Starlink in the end. However, Starlink is not the only thing out there. You know, the founder of OneWeb just announced a new venture, wants to launch 100,000 satellites. Others are going to do similar things. And I think this is really what we worry about. What's going to come next in absence of regulation and some understanding of what's sensible and what isn't. So that's what the community is working on.
The Schumacher-Levy comet was discovered by 3 amateur astronomers, Carolyn and Eugene Shoemaker and David Levy. It was really quite a find. What role can amateurs play in the role of analyzing, discovering, and tracking near-Earth objects? And I also forgot this from the beginning to ask this. How do you define a near-Earth object? How close?
Oh, so let me. So the near-Earth object is anything that comes within 1.4 astronomical units of Earth. Sorry, it's semi-major axis. Its orbit basically gets it fairly close to Earth. Your first question, the answer is emphatically yes. The amateurs, enthusiasts, especially people now with software and algorithm experience, can get involved in projects like these. One of the interesting things with LSST is that we are almost entirely dependent on computers and algorithms to both identify objects and images and to link them together to understand that they're asteroids. And this is something that typically astronomers don't, have as part of their curriculum. We're physicists who look up. That's kind of the definition of astronomer. We need computer scientists. We need software engineers to imagine these new algorithms and implement them. And secondly, the second aspect of LSST is all the data are public within the US and within Chile. So if you're an astronomer, if you're an amateur or just computer science enthusiast who has good ideas, you can actually get access to a lot of this data, to almost the entire astronomy, the entire asteroid data set, try to construct something better, try to improve on our algorithms, and discover objects on your own. So that's something that I really expect is going to happen, that we will have things like Shoemaker-Levy discovered, not necessarily by software that we've written, but even by software that someone maybe in this audience will write.
Mm-hmm. And Nikki, we only have a few minutes before we go to breakout. Maybe can you give us a quick sketch, an idea of future missions that you have planned and how they might be able to add value to early warning and being able to get information to NOAA so we can shut down transformers, those sorts of things?
Yes, I mean, practically, I would actually not practically, every mission that we have in the portfolio really has an impact on space weather, whether we're looking at something close to the sun, whether we're looking at something around the Earth, or whether we're downstream. So I even think of my Voyagers, the 2 Voyager spacecraft that have actually left the heliosphere and are out in interstellar space, but they're actually telling us what our whole solar system is about to go through in interstellar space. And so to a certain extent, they're kind of doing a super early warning of what the whole solar system is going to see. Is it space weather? Probably not, but I like to think of it like that. But all the way we have assets that we're putting at Mars. So we've actually taken over in the Heliophysics division, the RAD instrument on Curiosity to give us radiation data from the Martian surface. We have a new mission called Escapade that will launch in a couple of years. It's 2 small spacecraft going to Mars. They'll sort of start off in the upstream solar wind, and then one of them will precess around to behind Mars, and we'll actually be able to sort of get space weather data at Mars. And of course, that is as we are getting ready to support the Artemis program to send crewed missions first to the moon and then to Mars. For the moon, we are actually putting a space weather package called Hermes, and that is going on the first module of the Lunar Gateway. And so that's going to be providing environmental data for us, or space environmental data for us at the moon. We have a Punch that's going to be looking, we sort of say it's looking at the sun from the inside out, or the corona from the inside out. It's really focusing on the very low corona and then watching the storms as they move out. From there, we have sunrise, that's 6 little CubeSats that are going to go out and sort of spread out and form a giant radio telescope, or like a big sort of receiver in the sky, way bigger than anything we have the technology to fly. But these little CubeSats are going to just be able to give us the data, and we'll be able to reconstruct it on the ground to be able to sense all the radio signals and the plasma wave signals that are associated with the big events at the sun. So there's all those great things happening. We have Solar Cruiser, that is a tech demo of the largest solar sail that will fly yet. And again, that is actually a demonstration, hopefully, of a technology that will allow us to get spacecraft closer to the sun and sit in a stable orbit. Right now, there's a point about 1 million miles upstream of the Earth where the gravity of the Earth and the sun balance, and we can put a spacecraft there and it stays there. What we'd like to do is get it closer to the sun, get more warning that these events are coming towards us. So it's kind of something for everybody in the heliophysics division.
Absolutely. We're going to go to questions, but I just first want to say very quickly, thank you both for joining us today. This has been fascinating, a really good conversation. But I also wanted to mention Artemis is a program. It's the first woman and the next man to land on the moon, and we're going to establish a base there. And it's very, very exciting.
It
Nikki,
really
thank
is.
you.
It is a great privilege to be supporting the Artemis mission. I must say, it's wonderful.
Yeah. Mario and Nikki, thank you very much. We're going to go to questions from the field.
All right, the first question comes from Mark Sachs, who had a comment earlier that I think would be interesting to share with everyone, and then a question about video footage.
Which comment, Barrett?
Oh, your mention about the scenario that you developed earlier about taking everything offline.
Oh, yeah, briefly. And for those of you who don't know, I used to be the chief security officer at NERC, so the power grid, and was at Verizon prior to that doing national security work with the White House and others. And yeah, there's a lot of awareness of CMEs and effects it could have. FEMA and many others have done lots of really good studies. So there's a rich amount of information to read up on. The biggest challenge that we faced is not that we know how to respond, it's the willingness to respond. And for example, if we needed to turn off power for say 24 hours, would we be willing to do it? You know, would the White House, would others around the world be willing to tell their citizens, we're going to do without power for 24 hours so that we can turn it back on tomorrow versus going without for the next year? That's a gut-wrenching decision. And of course, all the naysayers, you know, the pundits out there will, half of them will say it was the right thing to do. The other half, back to our science discussion we had the last hour, will disbelieve everything and question the authorities. So but we have to be ready for something like that. And there's a lot going on in Washington. I don't live there anymore. I'm down now in Huntsville, where we are absolutely proud that we're building the new Artemis mission program here, building on what we did with Saturn V and many of the other systems. It's a really, really cool space-based town. Love it here in the Rocket City. And what was the other thing, Barrett?
Oh, you had a question about public video.
Oh, yeah. Those images that are stitched together about going around the sun, is there an actual video that was sent back, or is it just a sequence of pictures that are stitched together to make a video?
Honestly, it's a sequence of pictures, but they're pretty high resolution. But yeah, if you want to go to certainly, you can Google Parker Solar Probe. There's a ton of footage from there that you can see. There's a
Great.
Website.
Yeah, it'd be fun just to watch. I mean, because that's
Yeah.
something most of us can never experience. So we'd love to be able to see the live video. And thank you.
Yeah, the one that I showed you today is not public yet, so you're welcome.
Appreciate it.
You saw it here first.
That's right.
So the next question is from Ricky Solomon. Ricky, are you there? He asks, how good is the system to protect our transformers? Mass starvation does not seem like a good option.
No, it doesn't. I agree. And so they're certainly they are working very hard to harden the grids and be prepared. Again, knowing something's coming is a big one. But as Mark said, having the decision, do you turn it off? Do you keep it on is the bigger one. But they're certainly hardening up the grids for I believe that power grids that are in areas that sort of typically have to deal with aurora and typically have to deal with these currents overhead certainly take it very seriously. The Alaska pipeline, for example, is another piece of equipment that is regularly impacted by space weather because it sits under the aurora all the time. Sometimes you just see sort of current surges and you think there's something wrong with the pipeline, but it isn't. It's just a current flowing through, but it can also cause problems for the pipeline itself. It can cause corrosion. So people that have to live with it are certainly taking a lot of precautions to save that.
And then I think related question was from Sierra Salter. Did you want to ask your question, Sierra?
Yeah, sure. Can you hear me?
Yes.
Yeah, so there are a few research papers showing that the probability of another Carrington event is actually 12%, 1 in 8. So I'm just wondering if you can comment on that. And I've seen numbers from the Electromagnetic Pulse Commission saying that if this happens, 90% of Americans will die because we can't get food and water without electricity. I mean, I think those are the numbers like to discuss there. I mean, what do you think about that? And I requested a one-on-one with you, Nicola, if you're willing to talk, because I have some business plans related to this. Thank you.
Okay, yes. Yeah, I saw your request. We're trying to clear some space tomorrow. But yeah, thanks for the question. So it depends who you talk to, and somebody else popped in the chat there, over what time period, 1 in 8 over what time period. And it's because we haven't had a big event for 150 years. And so the Carrington event is thought to be like a sort of what they call like a 100-year event, like the 100-year flood event, that type of thing. And so because we haven't seen one, then the probability is going up that we will see one. So it's about 12% that we'll see one during this solar max, which is an 11-year cycle. And if you prepare and you protect the grids and you take it down in an orderly fashion, then it's a much less of a sort of terror scenario than some of the reports are saying. But if you were unprotected and you took no precautions whatsoever, then they are the type of things that can happen. Once you lose clean drinking water, that is a very big deal. It's not just the loss of the power grid, it's the sort of cascading effect that happens when the power grid goes down. So it's not just the power grid alone, but it's all of the other things that rely on the power grid. But that's why we're here doing the research we're doing and working with our partners to be able to accurately predict these events. And as Mark noted, FEMA obviously taking it very, very seriously and making sure that we have procedures in place to avoid anything like those disaster scenarios.
All right, so Evan asked, are there any new projects that look promising for redirecting large asteroids? I've heard of proposals to lasso and push them off target, but I don't know how legit that is. I know you've addressed that somewhat, but if you have any additional comments, we would love to hear them.
I think DART is the biggest project that's actually in the sky and is being tested right now. There are theoretical studies, there are papers coming out. I think a few months ago, I recall people looking at what could one do with nuclear weapons. Depending on who you ask, there's more or less skepticism on those types of ideas. But people are thinking. The issue here is sort of similar to what I believe Mark mentioned. This is a kind of event that's fairly rare, and it's until if you're trying to prepare something that happens once in 200 years or 300 years, it's difficult for humanity to think about those kinds of threats and to get organized around those kinds of threats and even conduct research about handling those kinds of threats. So you're going to see that for asteroid deflection, the level of research is fairly low. We're talking hundreds of millions of dollars levels, which is why a lot of the effort right now is on finding these objects first and finding them early, because if you actually know that there's one on course 60 years from now, then you can start changing the public opinion or I guess the general just sense of how urgent and important this is, and you suddenly see an explosion in the kind of research and experiments that that are needed for deflection. But I think right now most of the effort really is towards searches rather than deflection. A lot of the deflection efforts are still on paper.
All right, so Chuck Meyer asked, how much of the grid is currently protected?
Oh, golly, I don't know the answer to that one. I'm sorry. You would have to address that to NERC, and they would be able to tell you. I mean, certainly all of the power grid is protected against certain different things, ground-induced currents and various stuff. Actually, how much would be protected for a solar event? I don't know the answer, but I would say most of it.
Mark, did you want to speak to that? It looks like you have a comment in the chat about this.
Yeah, in general, most of the Earth's weather phenomenon, lightning storms and so forth, have a pretty big impact on grid operations, and there are breaker systems. All of you have probably experienced outages because of a local distribution site went down. These are safety breakers that are kicking in to protect the rest of the grid. So if a Carrington style or other solar thing were to happen again, we hopefully would have a little more notice than we would with a lightning strike. So preparations could be put into place. I've been looking for, but cannot find, a really cool FEMA study from a number of years ago that showed how it would actually play out based on the physics of the Earth and the physics of a large electrical event. And what they were finding was depends entirely on where the Earth is in its rotation, depends on the angle of impact, whether it hits over a continent or over an ocean. But in general, the east coasts of the continents would be the most likely to be impacted because of the oceans. But there could also be a skipping effect where it could hit the edge of a continent, go up, come back down, and hit the interior or the western edge of a continent. It's a cool report. If you're willing to Google around and find it, if I can never find it, I'll try and get it out to everybody. But it's worth reading.
Thanks, Mark. So we are out of time. It is time for us to move to our next session. Nicola and Mario, thank you for taking the time to be here with us. This is a fascinating conversation. Thank you for protecting us all from asteroids and solar flares and all of your hard work to that effect. We deeply appreciate you. Thank you, everyone. Thank you, John.
Thank you.
Thank you, Barrett. Thank you, John.
Yeah.